Pokok bahasan kita ini Deret Fourier waktu diskrit, ya, dan bagaimana hubungannya antara ya, deretan periodik dengan spektrum diskrit, ya, deretan diskrit dengan spektrum diskrit. Pokok bahasan kita ini, ya. Nah, seperti continue, ya, seperti sinyal continue. Ketika kita menganalisis di domain waktu sinyal continue itu bersinyal periodik, maka untuk mendapatkan analisis di daerah frekuensi, ya, koefisien Fourier-nya itu menggambarkan spektrum, ya, menggambarkan spektrum. Demikian juga di deretan diskrit, ya, sinyal waktu diskrit yang periodik. Untuk menganalisis di kawasan frekuensi, ya, kita membutuhkan analisis Deret Fourier. Nah, sementara untuk menganalisis di daerah frekuensi untuk sinyal yang tidak periodik, yang terbatas, tidak periodik, ya, yang tidak periodik, kita menggunakan transformasi Fourier diskrit Fourier transform, ya. Jadi diskrit Fourier transform sama Deret Fourier dibedakan oleh domain input sinyal yang periodik apa tidak periodik. Nah, yang menjadi tujuannya adalah bagaimana kita mendapatkan suatu spektrum di kawasan frekuensi diskrit. Ya, spektrum diskrit. Baik itu sinyal yang periodik dengan menggunakan tools Deret, maupun sinyal tidak periodik menggunakan transformasi Fourier diskrit Fourier transform. Ya. Dalam aplikasi kemudian untuk mempercepat komputasi, ya, kita mengenal yang disebut dengan fast Fourier transform. Ya. Jadi kurang lebih relasi transformasinya, ya, relasi transformasinya dengan mengambil satu perioda. Jadi tanda membedakan dia periodik tidak periodik dari suatu sinyal dan spektrum, di atasnya itu ada gambar kayak seperti sinusoid yang menggambarkan, ya, suatu deretan periodik untuk Xn, dan Xk itu suatu koefisien Fourier yang juga periodik, ya. Yang lebih itulah rangkuman bagaimana mentransformasi ke kawasan frekuensi dan mengembalikan ke domain waktu. Ya. Untuk mendapatkan, ya, arti dari suatu deretan periodik itu adalah memiliki nilai yang sama, yang berulang, ya, di kelipatan periodanya, ya, memiliki nilai yang sama di kelipatan periodanya. Ya. Kita tadi sudah memperkenalkan, ya, spektrum yang dinyatakan oleh koefisien Deret Fourier itu adalah penjumlahan satu perioda. Ya. Kita menganalisis satu perioda, ya, dari sinyal E pangkat minus J2 pi per N kali Kn. Ya. Jadi 2pi, nah yang perlu kita lihat di sini, minus menunjukkan arah arah jarum jam ya, ke bawah. 2pi per n menunjukkan 2pi-nya dibagi n sampel ya. Untuk yang ke K, untuk evaluasi yang ke K dari XK ini dijumlahkan dari seluruh domain N, ya, dari 0 sampai N-1. Ya. Nah, untuk mengembalikannya, ya, dia punya formula, ya, deretan periodik 1 per N, ya, dari XK, ya, dijumlahkan, kalau ini untuk ke N, ya, N-nya jadi sesuatu yang tetap, N X1, X2, ya, K dari 0 sampai N-1 dijumlahkan, ya, disuperposisi spektrumnya, tapi pangkatnya positif, E pangkat J 2πN per KN, ya. Ya. Nah, untuk mendapatkan koefisien Fourier disebut persamaan analisis, ya, tadi, ya. Nah, kita mendefinisikan suatu matriks WN, ya, WN, yaitu E pangkat minus J 2pi bagi N, ya. E pangkat minus J 2pi N, ya. Sehingga XN-nya WN pangkat minus KN, karena WN-nya didefinisikan sebagai E pangkat J 2pi per N, ya. Persamaan analisis adalah mengurai, ya, komponen sinyal menjadi spektrum, ya, sintesis menggabungkan, ya, spektrum itu menjadi sinyal diskrit, ya. Nah, kita menggunakan definisi Deret untuk menggambarkan, ya, untuk menganalisa kondisi periodik. Nah, sebagai contoh, untuk suatu deretan periodik impuls yang dia berulang nilainya 1 setiap kelipatan periodik, ya, ke N. Nah, ya, sehingga kita dapat XK, ya, karena WN pangkat 0, E pangkat, ya, minus J 2pi per N kali 0, E pangkat 0 itu sama dengan 1, ya, sama dengan 1, ya. Jadi deretan impuls periodik memiliki koefisien Fourier, daerah spektrumnya, ya, koefisien Deret Fourier-nya itu sama dengan 1. Dan ketika XK sama dengan 1, ya, maka XN-nya adalah, ya, impuls. Dan sebaliknya, jika spektrumnya, koefisien Deret Fourier-nya itu deretan impuls, ya, maka di domain waktunya itu sama dengan 1. Ya, sifat seperti ini disebut sifat dualitas, ya, sifat dualitas. Contoh suatu deretan periodanya 10, dia bergerak dari 0, ya, sampai 0 sampai 4, ada 5 titik nilainya 1, dan 5 titik berikutnya nilainya 0. Tapi periodanya muncul lagi di ke-10, berarti periodanya 10 ya secara periodik. Nah, kita menganalisis satu perioda ya, satu perioda ya. Spektrumnya, koefisien Deret Fourier yang menggambarkan spektrumnya ya. Penjumlahan n sampai 9, tapi karena 5 sampai 9 0, jadi cukup n sampai 4 ya. W10 karena n-nya 10, Kn ya. Kn. Nah, penjumlahan geometri seperti ini ya. Geometri seperti ini adalah 1 dikurang W10 pangkat 5K dibagi 1 kurang W10 pangkat K ya. Kalau dibentuk dia ya dalam bentuk sinus ya, dalam bentuk sinus ya, maka akan kita dapat ya yang di atas 2J sinus VK per bagi 2, yang di bawah itu 2J sinus VK per 10 ya. Nah, sehingga amplitudonya bentuk ya, sinus VK per 2 dibagi sinus VK per 10, fasanya adalah E pangkat ya. Fasanya adalah fasa linear terhadap K 4pi per 10. K ini adalah fasa. Ya. Kalau amplitudonya, amplitudo spektrumnya ya, digambarkan dalam bentuk harga mutlak ya, dia bentuknya ya fungsi dari K ya, fungsi dari K. Diskrit. Nah, ini yang kita sebut tadi, bagaimana kita mendapatkan spektrum diskrit ya. Spektrum diskrit, spektrum fungsi dari diskrit ke K ya. Juga periodik. Dan juga fasanya ya. Fasa diskrit, fungsi dari K ya. Sifat-sifat yang mendasari Deret Fourier ya. Dia bersifat linier, homogen terhadap suatu konstanta A dan B, dan mengikuti hukum superposisi ya, di superposisi. Kemudian pergeseran deretan ya. Kalau xn-nya digeser sejauh m ya, maka ada faktor wn pangkat km ya, digeser sejauh m. Dualitas tadi bisa dipertukarkan. Kalau deretan impuls periodik xk-nya 1 ya, dari contoh, dan kalau dibalik juga memiliki bentuk yang sama. Bentuk yang sama disebut dengan sifat dualitas. Juga memiliki sifat simetri ya. Memiliki sifat simetri ya, di dalam deretan konjugatnya dia menjadi konjugat minus K ya. Bagian real dari konjugat xn itu fungsi genap di domain frekuensi, bagian imajinernya fungsi ganjil ya. Kemudian didefinisikan konvolusi periodik ya. Konvolusi periodik ya. Dua sinyal periodik jika dikonvolusi disebut konvolusi periodik ya, maka perkalian di domain spektrumnya. kita masuk ke transformasi, ya, transformasi Fourier deretan periodik dan transformasi Fourier deretan periodik dan transformasi Fourier deretan terbatas, ya. Nah, kalau dia terbatas, kita menggunakan transformasi Fourier waktu diskrit, ya, kita mendapatkan suatu spektrum, ya, continue X E pangkat J omega, ya. Nah, kalau dia deretan periodik, transformasinya, ya, transformasinya juga periodik. Juga periodik. Nah, hubungan antara koefisien Deret Fourier dengan transformasi Fourier, ya. Ya. Ketika kita memiliki spektrum kontinu XE pangkat J omega, ya, XE J omega, nah XE J omega ini didapat dari suatu transformasi Fourier, ya, yang terbatas, yang tidak periodik, yang terbatas. Dari mana mendapatkan suatu terbatas? Dari, ya, yang terbatas. Kalau dia terbatas, maka spektrumnya adalah kontinu, ya. X E pangkat J omega, spektrumnya adalah kontinu, ya. Fasanya juga kontinu, ya. Nah, untuk mendapatkan koefisien diskritnya, ya, untuk mendapatkan spektrum diskritnya, bisa dilakukan dengan mencuplik amplitudo kontinu ini dengan mengambil 2 pi berapa sampel, ya, 2 pi berapa sampel, ya. Jadi kalau misalnya kita cuplik ini, kita cuplik di antara 0 misalnya, ya, kita cuplik 10 cuplikan, berarti 2 pi per 10, ya, seperti contoh tadi 2 pi per 10, n-nya 10, maka setiap 2 pi per 10 ada satu cuplikan, ya. Jadi artinya omeganya kita ganti dengan 2 pi per 10, ya. 2 pi per n, ketika n kita ambil 10, maka spektrum kontinu ini kita cuplik, namanya pencuplikan frekuensi, ya. Artinya sekarang kita bisa mendapatkan spektrum diskrit, ya, spektrum diskrit dari deretan terbatas, ya. Pertama dua cara, ya. Cara pertama yang ini adalah kita transformasikan ke Fourier, jadi X, E, J, omega, kemudian kita sampling, kita cuplik dengan mengambil 2 pi per n. Omega sama dengan 2 pi per n, ya. Namanya sampling frekuensi. Maka kita dapat spektrum XK-nya, diskritnya. Atau cara kedua, ya, cara kedua yang sinyal terbatas itu, ya kita bikin seolah-olah periodik, ya, seolah-olah periodik dengan periode n tertentu, ya, periode n tertentu. Kemudian kita gunakan analisis Deret, ya, tadi seperti contoh tadi Deret Fourier, ya. Maka koefisien Deret itu adalah spektrum diskritnya. Jadi dua cara. Bagaimana intinya? Bagaimana mendapatkan, ya, mendapatkan spektrum diskrit. Pertama melalui Deret Fourier diskrit, yang kedua transformasi Fourier diskrit, ya. Transformasi Fourier diskrit tadi, transformasi Fourier yang dicuplik, ya. Diskrit Fourier transform, ya. Sinyal terbatas seolah-olah dibikin periodik, ya seolah-olah dibikin periodik dengan periode n, sehingga spektrumnya kita ganti omega 2pi per n. Ya, inilah yang dilakukan dengan transformasi Fourier diskrit. Ya. Jadi kita cuplik, jadi titik-titik pencuplikan. Titik-titik pencuplikan dengan teknik omega ganti 2pi per n. Ya, kita cuplik spektrum frekuensinya, ya, sehingga dapat domain diskrit, ya, spektrum diskritnya. Ya. Jadi dua cara, yaitu yang kita sebut dengan pencuplikan terhadap transformasi Fourier. Ya. Ya, cara kedua itu pencuplikan terhadap transformasi Fourier. Nah, berikutnya itu dikenal sebagai transformasi Fourier diskrit. Bagaimana mendapatkan spektrum diskrit dari pencuplikan, ya, transformasi Fourier-nya. Ya. Ya, pencuplikan terhadap transformasi Fourier. Nah, jadi kalau kita memiliki, kenapa penting ini? Ya, karena input bisa saja periodik, bisa tidak periodik. Ya. Sistem, ya, biasanya memiliki deretan terbatas. Bagaimana menganalisisnya di dalam domain diskrit? Ya, domain diskrit. Nah, kita mendefinisikan WN tadi, WN, ya. Kalau ini 8, WN tadi arahnya, contoh N8, ya. Berarti di 2V dibagi 8 sampel. Jadi ini WN0, ya, W80, W81, W82, W83, W84, W85, W86, W87, W88. Ya, balik lagi dua putaran, 9, 10, 11, 12, 13, 14, 15, 16. Ya. Contoh W4, berarti 2 pi dibagi 4. W0-nya, W40 itu sama dengan 1. Kemudian di sini W41, W4 pangkat 1 itu adalah min J, ya. W4 pangkat 2 itu min 1, W4 pangkat 3 dia J, W44 1, ya. Balik lagi, W45 dia min J, W46 dia min 1, W47 dia J, 8 dia sama dengan 1, ya. Nah, ini bisa menjadi bagaimana kita mendapatkan suatu sistem, ya. Bagaimana kita mendapatkan suatu sistem, ya, ketika XN, ya, input dikonvolusi dengan konvolusi dengan respon impuls, dapat spektrum diskrit, ya, dapat spektrum diskrit. Nah, itu menjadi suatu perkalian. Ya. Oke. Ada pertanyaan? Ya. Ya. Ada pertanyaan?
Belum ada, Pak.
Ya. Jadi intinya bagaimana mendapatkan spektrum diskrit? Ada dua, ya. Ya, ini kalau dia periodik kita menggunakan Deret, kalau dia tidak periodik kita menggunakan sampling frekuensi yang disebut dengan Diskrit Fourier transform, ya. Kalau dia periodik sinyalnya, ya kita menggunakan Deret Fourier diskrit, ya. Nah, transformasi Fourier diskrit ini di dalam kalkulasi algoritmanya, karena dia mengandung perkalian, ya, yang banyak, pangkat n, dan penjumlahan juga yang banyak, maka algoritma untuk menyelesaikan itu yang kemudian dikenal dengan Fourier transform. Baik, kalau nggak ada, kita
Hi students, welcome back to DSP online video lectures. This is the second video lecture on discrete Fourier series. In this video lecture, we would see some examples of discrete Fourier series that we have already studied in the previous video lecture. In addition to that, in this video lecture, we will also study the relationship between the discrete Fourier series of a periodic discrete time signal and DTFT of one period of that periodic signal. Okay, these are the two things that we will try to cover in this video. Let me move on to the desktop sharing mode and do the write-up on the OneNote book. Okay, let us start with quickly revising what was the DS expressions for DFS, discrete Fourier series, that we have got in the previous class. So periodic signals, discrete time periodic signals we are considering. Okay, and that if you 1 by n over k varying from 0 to n minus 1 x tilde of k, as you notice that this is a discrete time signal we are getting. Okay, this Fourier transform discrete Fourier series is a discrete time signal. We are using the square brackets to represent that. E power j 2 pi by n times k and n, right? Then the expression for x tilde of k, the discrete Fourier series, you could write it as n varying from 0 to n minus 1 x tilde of n e power minus j times 2 pi by n into kn, right? So we also, I just mentioned there the periodicity, the relationship between periodicity and discreteness. Okay, because x tilde of n is both, so the duality exists. If your signal is periodic, you get here a discrete time signal, and if your signal is discrete, then you would get a periodic thing. See, the reason is very clear. If you have a periodic signal, while you are expressing it in the frequency domain, you have the fundamental frequency and its harmonics. So those are the discrete frequencies are there. That's one reason when your signal is periodic, in the frequency domain, it will have discrete frequency components. Now consider the case when your signal is discrete, then what's going to happen? Recollect what we did in case of sampling. Okay, this is equivalent to kind of convolving with an impulse train, and thus convolution is equal, so multiplication with the impulse train in the time domain equivalent to convolving with the another impulse train in the frequency domain, that giving you multiple copies and thereby periodic. So this x tilde of n being both discrete and periodic, right? Like you could notice that x tilde of k, the DFS, is both discrete and periodic. So that's the duality. Well, that's just a detail. Let's work out an example now. Very basic example we will take, right? So what shall we do is compute the discrete Fourier series of a periodic impulse train. Okay, the which you could represent it by x tilde of n is equal to, that's a periodic impulse train. That means you have, let's say, r varying from minus infinity to plus infinity times delta of n minus r times n, where this r is an integer, could be an integer. Okay, that's what we need to do it. So just let's get a bit more feel about what this function is exactly. So assume some n value. How does it look like? It's a discrete function and a periodic function. Okay, assume that this is your 0. Okay, this has a, for example, a some unit sample at 0, right? Sorry, there is no need for an arrow mark there. Okay, so that's a simple, you call this as having one value. So it is periodic with a periodicity of n. So when will that delta inside function would again become 0 for varying values of r? So for example, again at the value n equal to n, small n equal to capital N, you have a value of 1 there, and so on. It will go, for example, then at 2n, this value is 1, and so on. R can take negative values also. Okay, so again at minus n, that function has a value, okay, minus 2n, and so on. That value is 1. So that's how the function looks like. This is your x tilde of n, right? So that's period. So you need to take that function from 0 to n minus 1 is one period of it. Okay, this length is n, that's being the periodic. Okay, this being 0, right? Let's first write the expression for x tilde of k is equivalent to summation over n varying from 0 to n minus 1 x tilde of n into complex exponential of e power minus j 2 pi by n kn. Notice here this value is n minus, so if you want me to write, this value is n minus 1 here. Okay, along the for when you consider one period of it, this is only, this has value, only value is 1 when n equal to 0, out of 0 to n minus 1, and 0 otherwise. So that summation turns out to be just making use of one term there, isn't it? That too when n equal to 0. So when n equal to 0, what happens to the complex exponential? That's equal to 1. Is it not? E power j 0, that's equal to 1. So what did we get here? How does that look like? Well, k here, if you call it, it's again periodic with a periodicity of, well, you call it as 1, same n, right? 0, 1, 2, so on up to n minus 1, okay, then n, and so on. So everywhere this is going to be 1 irrespective of your value. So that's so on here on both sides. Okay, so it's up to you how you periodicity you would attribute, but for sure capital N would be the periodic. This is a very particular case. Okay, this value is 1. That's how your x tilde of k would look like. What does that mean? If you want to generate an x of n that has value at only 0 and 0 everywhere else, you would require all the frequencies to be present. That's one kind of interpretation you could make out from it. Okay, so let's make a, from this, let's extend it a little bit more. Now suppose what you are given is, for example, you are given that x tilde of k equal to 1, and you do the reverse calculation now. Then if you want to compute, let's compute x tilde of n. Notice we already know the value, so first whatever summation we get here, that we are going to equate it to whatever x tilde of n that is there. So we started with impulse train, we got the DFS as 1. Now we start with DFS and of 1 and try to calculate the inverse DFS of it. So how could we represent x of n? That's equivalent to 1 by n times summation over k varying from 0 to n minus 1. Okay, and x tilde of k into e power j 2 pi by capital N times kn, correct? And this always 1 irrespective of the k value, correct? So all you have now is a complex exponential summation. So I could have kept tilde there, 1 by n into k varying from 0 to n minus 1 exponential of j times 2 pi by n kn. This is a very interesting summation. Let's take n equal to 0, right? Suppose if n equal to 0, okay, what would happen? This inside expression is equal to e power j0 is 1. You are taking summation of n such terms, so that means 1 plus 1 you are adding up n times, okay, n terms, so that would give you n summation, and that's equivalent to 1, right? If n is not equal to 0, that means any value of n in between n minus up to n minus 1, in fact, okay? And after that, of course, this being periodic, the values would repeat. Obviously you know the value now, okay? How do you know that? Because this is the DFS of the impulse train, which is 0 at 1 and all the rest of the places it is 0. So from that expression you know that now what is x tilde of n. This is for n equal to 0, x tilde of 0 is that, and now x tilde of n, which is can be written as 1 by n times k equal to 0 to n minus 1, okay, e power j 2 pi by capital N kn is going to be equal to 0. A very important result that we keep using at different points right away, okay, different problems right away. Well, what I am not going to attempt here is to make a rigorous proof for it, okay? One way we already have seen it. We started with the impulse train, we took DFS, so now we are taking inverse DFS and making it equal to impulse train. So that way there is no ambiguity there, but we could in fact do the same proof here rigorously, but that's not is of interest for me at this point. I would rather just show you like diagrammatically why does it, for example, would be equal to 0, okay? For example, you take n equal to 2, okay, then for example you could take a small n value for n equal to 1. How does it look like? The summation expression would look like k equal to 0 to 1, correct, e power j 2 pi by 2 times k, correct? So this is e power j pi k. J0 is, for example, if you this is how it is, its magnitude is 1, right? I am taking here the axis here, so this is 1. This is for let's say k equal to 0, its magnitude is 1, and k equal to 1, its magnitude e power j pi, right? So it is rotated by an angle of pi here, and that's minus 1. The summation is in fact equal to 0. So that's equal to 0, you could see it. And for all even values, this is how it would look like. For example, if you take n equal to 4, this turns out that you are going to sum here of equal proportions, okay, this. So in opposite directions those are there and they get cancelled out, okay? So this, for example, would be k equal to 0, one possibility, k equal to 1, k equal to 2, k equal to 3, okay? That's what could happen. Of course, those things could vary slightly if you are changing, for example, n equal to 2 and n equal to 3 here. The correspondence would vary, but the vectors would remain the same in the summation, okay? And what could be also interesting is to see a case when n equal to 3, okay, and I leave it to you to work out. You would get something like this then, okay, with an angle of 120 degrees here, 120 degrees here, okay? These are of all equal magnitude, so that might not be immediately obvious to you, but again in the electric circuits and networks, three-phase, when you have equal magnitude, then you worked out and have seen that the summation is equal to 0. So say the same thing, vectors, if you add them all together, you could prove that that will be equal to 0. Okay, and I repeat, we keep using this result right away in some of the problems. In fact, one of the exercise problem I would give you would require this: k equal to 0 to n minus 1 e power j 2 pi n. So let me write the expression here: 1 by n summation over k equal to 0 to n minus 1 exponential of e power j 2 pi by n into kn, right? This is for n varying from 0 to n minus 1, okay, is equal to 1 if your n equal to 0 and 0 otherwise. This is the result, very important result. Okay, right. So with that, let's move on to some other problem, next example. Okay, example 2. Now what we would consider is computing an inverse DFS. Again we will consider. Now assume that you have a function whose DFS is equivalent to r is varying from minus infinity to plus infinity n times. Now your DFS is an impulse train. That's what, instead of that original function in the time domain being an impulse train. And again, if you notice, we have purposefully considered multiplication by capital N. If this is 1, so then compute what is the value of y tilde of n. Okay, so let's do that out. Y tilde of n is equal to 1 by n. I am not going to draw that now again because I already did it in the previous example. Okay, your k varying from 0 to n minus 1, I need to take here y tilde of k e power j times 2 pi by n times kn, right? What happens to y tilde of k? Well, that has value only, for example, k varying from 0 to n minus 1, only at k equal to 0 it has a value, and that value is in fact equivalent to 1. All the rest of the places that value is 0. And what about this complex exponential value at k equal to 0? Because that's only when y tilde of k is not equal to 0, right? And well, that's equivalent to 1, so multiplied by 1 would remain same, and so you have 1 here. Okay, hope you could already see the duality relationship that is existing here. I will quickly point it out here. Take a look at these two expressions. One is a sign change is there here, so for example n replaced with minus n would give you this complex exponential. It's equivalent to flipping the signal. And then there is a multiplication factor of 1 by n. If you do that multiplication, you get it right away. Okay, and now come back to this expression. Well, flipping the signal doesn't matter because that's a symmetric about 0, because it's the impulse train is there on both sides. All you need to do is now multiplication by n should give you the inverse DFS. So duality between x tilde of n and x tilde of k is there. Okay, hope that's clear. It's up, I leave it to you. If you want, you could make a proof of it as well. Okay, that's not difficult. You did it earlier, I think, for some other examples, right? So let's take a brief pass from the examples now, and let's do another interesting stuff now. The second part, as I was mentioning, what we are going to study is DFS versus DTFT of one period of x tilde of n. This relationship is what we are going to explore now. Okay, what does that mean? Let me draw some signal. For example, assume that, let me first start with x tilde of n. Okay, for example, I have a signal something like this, 5, assume some value 5 4 3 2 1. Okay, 0 1 2 3 4. What's the periodicity of the signal? Yeah, the periodicity is n equal to 5. Okay, and then it's a periodic of 5. That means after that the signal would repeat here. So again 5 4 3 2 1. Okay, and this would continue. Same thing here. This is placed at 5. Okay, and now this would be placed at the same thing would start at -5. So if I want to draw from here in the reverse direction, this would be 1 2 3 4 5. This is -1 -2 -3 -4 -5, and this would continue on both sides. This is the x tilde of n, correct? This is x tilde of, what happened? I think this is stopped working now. I have to, okay, good, it started again. Okay, x tilde of n, I would like to take the DFS of it, which means the DFS of it is x tilde of k, correct? And what I would like to do now is, for the signal, you take one period of the signal. Okay, that means, for example, 5 4 3 2 1 0 1 2 3 4. This is what I would consider as, let's say, x of n. To this, let's compute the DTFT of this signal. Okay, for all other values, let's say this is going to be 0 on both sides of this indices. Okay, this is all 0, and let's call this as x of e power j omega. What we are interested is to explore how are they related. Okay, this is what we would like to explore, right? Let's start with writing the expression for x of e power j omega. Hope you all still remember the DTFT expressions. N varies from 0 to infinity, right? Well, here one period is what we are considering. Beyond that, that's 0. So I would just simply consider n varying from 0 to n minus 1 here. And then x of n into e power minus j omega n. Well, in the range of 0 to n minus 1, x of n is same as x tilde of n. So I would right away write it as x tilde of n, because both are same within one period. So no harm in writing it that way, into e power minus j omega n. Now let me write the expression for x tilde of k for the first signal. Okay, so x tilde of k is equivalent to, here again I take it in one period, 0 to n minus 1, x tilde of n into e power minus j times 2 pi by n times kn. Okay, let me write this k inside purposefully, k times n. Now, how are they related? Can you see any relationship between them? So simply you substitute in place of omega 2 pi by capital N times k, you are getting that. So this is a very important, crucial result, which we would come back again after a few more classes. Okay, just make a note of this relationship, and we will discuss it in more detail later in the next few classes. So x tilde of k, if I give you x of e power j omega, all you need for one period of the signal, all you need to do is, in place of omega, wherever the k value at which you want to find out, in place of omega you simply substitute 2 pi by n times k. That would give you the x tilde of k. In other words, your x of e power j omega a dtft is always continuous and dfs is always discrete, and of course both of them are periodic. The way, and dfs is nothing but, in this particular case of construction of x of n and x tilde of n, is just a sampled version of x of e power j omega. The samples being taken at omega equal to 2 pi by n times k. Okay, so let's work out another example here. I think this is example 3 on this problem. What should we work out? Let me give you one signal, x tilde of n, let me give you. Okay, for that let me also mention you that the periodicity of the signal is 10. Okay, starting let's say at 0, then let's say this magnitude is 1 here, 0, 1, 2, so 4, 5. Assume that for 5 values, 1, 2, 3, 4, it's 1, and then followed by that 5 zeros, 1, 2, 3, 4, 5, and that's the signal, n equal to 10. Then it is starting, so assume that then it has 1, 2, 3, 4, 5. Okay, and of course then this would continue. Okay, this is essentially, this is your signal which is periodic, and that's repeating. Okay, this value being 9. Okay, and of course here 1, 2, 3, 4, 5. Okay, and of course if you want me to draw 1, 2, 3, 4, 5. Okay, minus 1, minus 2, minus 3, minus 4, minus 5. Okay, you just 1, 2, 3, 4, 5. Okay, this is minus 5, minus 6, minus 7, minus 8, minus 9, minus 10. Right, so obviously it will be placed at minus 10. This would be placed at 10, and it would continue here. Okay, only thing may be, hopefully, okay, that's not bad. Let me extend it a bit. Okay, that doesn't look too good, that's too much crowded. Okay, let me slightly erase that out. Okay, let me quickly draw that. Okay, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then this will repeat. Okay, that's good enough. Now this is your, this value being 1, and this is your x tilde of n. Okay, let's take this, so if I draw only this, that would represent my x of n, the rest being zeros. Okay, let's first calculate what is x of e power j omega, n varying from, it has 0 to 1 period I am taking, so 0 to 4 only here, correct, and that value is 1, that is x of n into e power minus j 2 pi, sorry, I am writing for x of e power j omega, correct, there is no 2 pi here. What would come there? E power minus j omega times n, correct, that's what I would get. This is a geometric series with n varying, so what do we get? 1 minus r to the power of n, so that's equal to minus j omega times 4, minus j omega 4, no, there are 5 terms in fact, so that's equivalent to e power minus j omega times 5 by 1 minus r, that's equal to 1 minus e power minus j omega. The moment you see such expression, the first thing you would do is take half of them, half of it common on both numerator and denominator, right? So what do you get there? E power minus j 5 by 2 times omega in the numerator, in the denominator e power minus j 1 by 2 times omega, right, and in the denominator you get e power minus plus j 5 by 2 omega plus e power minus j. Okay, that would give you 2j in the numerator and denominator gets cancelled out, and you will end up here sine of 5 by 2 times omega by sine of omega by 2. Of course, I could further simplify this 5 by 2, if I take it to the numerator, okay, that would give me 4 by 2, that means 2, that means this is equal to e power minus j times 2 omega into sine of 5 by 2 omega by sine of omega by 2. That's your x of e power j omega. Okay, this is what I got for x of e power j omega. Okay, now suppose if I compute x tilde of k, I leave it to you to work out directly for this, but what I would in fact do here is to just write it by interpreting this value, but you do validate whether that is correct or not by calculating in the similar lines the way we did for earlier examples. So if I do substitute here, omega equal to 2 pi by n, or n here is 10, okay, 2 pi by n into k. If I substitute that, then what I would get is x tilde of k. That means the x tilde of k is e power minus j times omega in place 2 pi by 10, you substitute there, so that would give me 4 pi by 10 times k. Okay, this just adds to the phase only, right? And then sine of omega is 2 pi by 10, so 10 this goes, and then I guess you should be getting something like pi by 2 times k, is it not? 5 by 2 into 2 pi by 10, right? So 2 gets cancelled, so this what you get is pi by 2. Okay, and let me erase this out, not required. Okay, so that's what you would be getting in the numerator. Similarly here, if I am not wrong, 2 gets cancelled, sine of pi by 10 times k. Okay, in the class we discussed how to draw them, so I will not again repeat that, but let me just quickly point out what's the value of it you would get at omega equal to 0 or k equal to 0 for x tilde of k. So you write it them as sinc functions, so if I am not wrong, you would get around 5 there, because sinc is sine of pi by 10k by pi by 10k here, so that 10 will be there on the top. Okay, to create that. Similarly pi by 2, you do that out. So let me show you the some graph here. Okay, let me move to here, right? So this I'll just continue here. This we are done with, similar stuff. This example we are done with. Okay, and now we are here, so let me show you this. Okay, right, so the same thing I am showing here. When you are calculating, yeah, this calculation we are done with it. Okay, this is what is going, this is again the result from the textbook. You have a sinc like function there, and you could notice there now, depending on the n value, okay, those many samples, 2 pi by 10 into, if you are taking n is 10, you are taking 10 samples of one period of that signal. That's what it means. Okay, if your n is 100, that means you are taking 100 samples of your x of e power j omega. That x of e power j omega is computed for one period of your discrete time signal. So that's what you could observe here. By the way, you notice here in some places this arrow marks here, those are the places where you do not know the phase, because that function becoming 0, that phase is unidentified. For that you keep a cross mark. That's all. So this example also we are done with now. Okay, and so how much time it has taken so far? Let me check that out. So this is so far 35 minutes. Okay, so let me just take 10 more minutes to work out one more example, and give you another as an exercise. Okay, so let's do that out. Okay, this example we are done with it. Now this is example 4. Let me work it out. So far we have not done any examples where we have eigenvalues, eigenvectors. Okay, so that's what I will do it in this example. So let's consider a continuous time signal which is given by a times cos of 200 pi t. Okay, this assume that this is sampled, the signal is sampled at a sampling rate of fs equal to 1 kilohertz, right? And then what I would like you to do, what I would be in fact doing here is compute the discrete Fourier series of the resulting periodic discrete time periodic sequence. Okay, that's what we are going to do now. Okay, so what's your time period here? Time period is nothing but with which you are sampling is 1 by fs, right? That's being fs being 1 kilohertz. This is equivalent to 10 power minus 3 seconds. Okay, now how do you get this periodic sequence of x tilde of n? That's nothing but, you know, the rate at which you are sampling, so that's equivalent to xc of nt. Okay, so that would give you a times cos of 0.2. So let me write it as 2 pi by 10 times n. Is it not? Okay, then tell me what's the periodicity of this signal, right? For n equal to 2 pi omega, so your n here periodicity is 10 here, so that's periodic with a periodicity of 10, right? Then how do you solve now? What is it that you need to do? You need to find out the DFS of it. So something should ring in your mind the moment you see cosines and sines. They can be written as complex exponentials, and the whole stuff here, the definitions of x tilde of n and x tilde of k are in terms of complex exponentials. So that's how you should proceed. That makes your problem solving easier. Okay, so first you write it here, what we know about how x tilde of n should look like. X tilde of n is equal to 1 by n, k varying from 0 to n minus 1, right? And then x oops, I picked the wrong one. X tilde of k into e power j times 2 pi by n into kn. Okay, so you have complex exponentials which are positive. That's what you need. Now try to write that out in that manner. So how can you write a times cos of 2 pi by 10 times n as a complex exponentials? So that's equivalent to e power j plus e power minus j, which would give you a by 2 times exponential of j times 2 pi by 10 into n plus e power minus j times 2 pi by 10 into n. You notice here you need all of them as positive here. So can you somehow express this as a positive exponential, 2 pi by 10 into n? Okay, this is periodic with a periodicity of 10. So can I write in place of this, okay, 2 pi by 10 into k? For example, here the k value is 1, so it's periodic. So what I could write here in fact is 2 pi by, this is also equivalent to e power minus j, 2 pi by 10 into n into 1 minus 10. I'm taking minus 10 because then minus 9 I would get, and this 2 get cancelled out. Okay, hope you are following it. This is k, both k and n, you could add the periodicity, right, of n, and you would end up with those are the two properties we discussed in the last video lecture. So then this is equivalent to e power minus j 2 pi by 10 into n times 9. Okay, now let me write the full expression here. In the similar lines to expansion of x tilde of n here, let me write it in that way. So what do I have for x tilde of n now, which is a cos 2 pi by 10 into that. As if you want me to write as 1 by 10 into, for example, that's there inside. Okay, so if I divide it, I need to multiply here. So 10a by 2, that's nothing but 5 times a. Okay, e power j times 2 pi by n, that's 10 here, into 1 time n, right, and plus again 5a here, 5a into wait a minute, this has become, sorry, I forgot to change it. So this negative has become positive there, e power j times 2 pi by 10 into 9 times n. Is it not? That implies, so if you expand it for all the terms of k, you would see that x tilde of k is equal to 5a when your k value is equal to 1, or it is equal to 9, right, and 0 otherwise. That's all. So if you want me to draw that, how does it look like? Your k, okay, 0, at 0, this is, assume that a is something positive, let me draw it this way. Okay, at 9 again I have it to be 5a. Okay, then in between this is equivalent to 0. Similarly, when I keep a copy here, I would in fact get a, then this is periodic on both sides. This is how it looks like. Okay, hope this is, sorry, a small correction here. This is this in fact is 1 here, sorry, this is 0. Okay, and if I keep another copy here, essentially what would happen is this would be symmetric here. Okay, this would be at minus 1, whichever is there at 9 would come there. Okay, and then these values are 0 here. So this is how it looks like. Okay, that's all for this problem, and I will end this class with giving you an exercise, which is second exercise for you. Slight extension to this problem. Now I am modifying my continuous time function with one more term, a times cos of 200 pi t plus b times cos of let me write 500 pi t. Okay, this is the term I am taking. Assume that this is what is been sampled. I still keep the same sample rate of ft fs equal to 1 kilohertz. Okay, that's the rate I am sampling it. Okay, now you need to do the same thing. Now see, the moment you have two functions, you need to look at what is the time periods of each of them, and then you need to LCM of that would give you the common thing. So based on that, you work it out. You already did some of similar things. So yeah, by the way, let me complete that question. You compute the DFS of resulting compute the DFS of the resulting discrete time periodic sequence. Okay, you do that out. If you want, you could also compute, for example, the DTFT for one period of the signal, also compute DTFT for one period of that discrete time signal, which is periodic because, okay, and verify the relationships, okay, and that you, so that itself is the solution for you. If they are matching, you did it correctly, and verify its relationship, with x tilde of k. Okay, hope I have given you the another. Okay, I didn't give you any other exercise earlier. That's okay. You do this out. Yeah, I should have given one more. So let me give hope. Yeah, let me take few more minutes. So first exercise, let me write here. I thought I have given before starting here, but I didn't do that. Okay. Yeah. So I'll quickly write that out here. Another exercise for you is, you are given, for example, this the derivation of your DFS itself is the exercise I would like to give to you. Okay, so let me write that exercise here. So yeah, in my write-up that I would post, I would move it to the top. So I'll still write it as exercise 1. So suppose if your x tilde of n is equal to 1 by n, so one of them you define as that. So this is varying from 0 to n minus 1, x tilde of r into e power j 2 pi by n times rn. Okay, then you need to prove that x tilde of k equal to n varying from 0 to n minus 1, x tilde of n into e power minus j 2 pi by n times kn. Okay, this is then. Okay, some hints here. You start in fact from here. Okay, you start from here, you multiply. So this is what, on the right hand side of this expression you substitute x tilde of n. Okay, and then you try to simplify it, and one of the expressions that we have written earlier would come to your help here. For example, this is the expression would help you to figure out. Okay, and then you will end up with having just and once you are substituting and simplifying the right hand side of it, you will be left with this simple x tilde of k. Okay, that's all for this class. Yeah, sorry for slightly long video, but with that we are done with these examples. Okay, and let's, in the next video lecture, what we would do is we would work on some of the properties of DFS. Okay, I'll stop here. Thanks for watching and see you in the next video lecture. Bye. Take care.